everyone, Mrs. Pasega here, and today we're going to talk about electric field versus electric potential. Both are ways to help us visualize how charge distorts the space around it in ways that you and I can't see with our eyes. This distortion creates both electric field, which in turn creates electric force, as well as electric potential, which in turn creates electric potential energy. So let's talk about what this means. And we'll start off with the more familiar field theory. The important thing, big idea number one, that you should know is that fields could cause forces. Let's take the gravitational field. We take the gravitational field of the Earth. If a mass is brought into that field, that mass would experience a gravitational force. So the same must be true for charges. If I have an electric field that distorts the space, a charge that's brought into that field could experience a electric force. Aha! Now let's look at that a little bit more closely. Fields can exist independently of other objects. A single object on its own, like the Earth, creates a field. So let's say I have a field G and it's distorting the space around the Earth. The green down here at the bottom is going to represent the Earth and its curvature. These lines pointing towards the center of the Earth are my gravitational field. If I bring a mass, like a baseball, into that field, that mass now experiences a gravitational force because it's in a force field. As a result of that force, the ball accelerates towards Earth because forces cause mass to accelerate, or at least unbalanced forces do. So now let's write down the similar statements for electricity. Let's say that we have a charge distribution and it creates an electric field. That field distorts the space so that if another charge were brought into that space, that charge would experience an electric force. And the electric force could be used to figure out how fast that particle accelerates. Let's take a look at this field line diagram, which you should be familiar with at this point. Pause the video and ask yourself this question. What are the signs of charge on P and Q? Here's what I got. I got both P and Q are positively charged. I know this because my lines point away from positive charges. So in this case, my field line points away from P. P must be a positive charge. It points away from Q. Q must also be a positive charge. So now let's say I bring a particle in, a positively charged particle. That positively charged particle is now in distorted space and experiences a force. The force goes in the same direction as the electric field because imagine that this positive charge is being repelled by a combination of P and Q. It's being repelled a little bit harder to the left than the right because Q has more charge than P does. I can tell because it has more field lines. But what about the force if I put a negative charge in this field? Where would its net force be? Please note that a positive charge moves in the same direction as the field lines, but a negative charge actually moves in the opposite direction. This negative charge is attracted to P because negatives are attracted to positive. So it does cause this mass to accelerate because there's a force on this particle. Okay, so here's what we are trying to picture. I'm trying to picture that there's a distortion in space. This distortion represents two positive charges. They distort the space upward, away from what I'm going to call a neutral ground, right? If you follow with your eyes where these white particles are moving, these represent the paths of positive charges. Guys, those little paths, the white dots, those are the field lines. So let's take a look at this more closely. I've got a positive charge in this situation and a negative charge. Maybe this is our P and Q from the previous slide. they would each experience a force. In this case, our positive charge would get repelled away from the other positive charges. Maybe it moves down the hill, something like this. And the negative charge would be attracted to the positive charges and it moves up the hill. So we can use field lines to show where particles might move. Another interpretation, however, is what if we use the height above the ground? What if we use this as height, similar to how we use height in gravitational potential energy? Oh, well, that's kind of useful because then I see that there's a positive height, a positive potential energy for our positive charge. It would have electric potential energy. And because of its electric potential energy, if you release it from rest, it'll speed up and gain kinetic energy. Notice that at this height, any particle put at the same height would have the same electric potential energy. So we're going to call this a potential. Potential is going to be like a height. Let's take a look at another charge distribution. This is the charge distribution of a dipole, and it introduces big idea number two. Big idea number two is that this distortion of space could be represented two different ways. We're trying to represent that negative charges distort the space downward, positive charges distort the space upward. And if we view it from above, we could draw the field lines. The field lines would represent the path of these little white particles. There we go, my field lines. But we could alternatively use equipotential lines, lines at which it's the same height above the ground. That means you'd have negative potentials near negative points, positive potentials near positive points, and you'd have points along the same line all having the same potential. So instead of having field lines, we could have potential lines, whereas fields point away from positive charges and toward negative. One drawback is you can't really get numerical data from it. Field lines are nice because they can tell you if charges are positive or negative. They can tell you which charge has the larger magnitude. It can even tell positions where the stronger field is. But it can't tell any numerical data from this. Here's what potential lines do instead. With potential lines, this represents different heights above or below the ground. So do you see where I have this negative 10 volts? That must mean there's a negative charge in the center of that somewhere. In this case, negative potentials mean those are near negative charges. Positive potentials mean you're near positive charges. In this case, I know there's two negative charges, and they're probably each in the center of these green circles. It still has this idea of more lines means stronger field. In this case, that means that when my lines are close together, right here, there's a stronger electric field than over here. But I can actually get numerical data and use that to help calculate electric potential energy, which is what we'll do in block 3. Just like field lines, these equipotential lines do not cross each other. That would kind of be like you can't be at two different heights at the same time. That wouldn't make sense. And what each line represents is how much height above or below neutral space that distortion is. So try out homework 6.2. It's going to have problems with both electric field and electric potential, and we'll recap this in block 3. Good luck!